When a particle moves along a smooth curve, the tangent vector turns as the curve bends. And recall that we showed that the tangent vector is the rate of change of the position vector along the length of the curve. And the length of the unit tangent vector remains constant because it's a unit vector with the magnitude of 1, and only its direction changes as the particle moves along the curve. Now the curvature, denoted by kappa, is the rate at which a tangent vector turns per unit length. So we have the derivative of the tangent vector with respect to s, and the curvature is a scalar quantity, so it's the magnitude of this derivative. And if the smooth curve is already defined by the position vector as a function of the parameter t, then using the chain rule, we can write the curvature as a derivative of the tangent vector with respect to t, while the derivative of t with respect to the arc length parameter. So recall that the magnitude of a scalar multiplied by a vector is equal to the absolute value of the scalar by the magnitude of the vector, being the derivative of the tangent vector with respect to t. And recall that the derivative of t with respect to s was equal to the reciprocal of the magnitude of the velocity vector. So we can write the curvature in terms of the parameter t, where t hat is the unit tangent vector, which can also be written as follows. Given the tangent vector t has a constant length, being a unit vector, then as we found previously, for vectors of constant length, the dot product between the vector and its derivative is 0, meaning that the vectors are orthogonal. Now also recalling that the curvature is the magnitude of the derivative of the tangent vector with respect to the arc length parameter s, then a principal normal vector, which is a unit vector, is equal to dt ds, being the orthogonal vector to the tangent vector, divided by the magnitude of this vector. So therefore we obtain the reciprocal of the curvature by the derivative of the tangent vector. And this is the principal normal vector for a smooth curve in the plane, where the curvature is not 0. Now this vector points in a direction in which the tangent vector turns as the curve bends. So if we face a direction of increasing arc length, as the tangent vector turns clockwise, as we can see, so from this tangent vector to this one, the normal vector points to the right. So the normal vector points to the right as t turns clockwise. And in contrast, if the tangent vector turns anti-clockwise, so if we take a unit tangent vector over here, so therefore this tangent vector is turning anti-clockwise, then the normal vector points to the left, which is the case over here. And simply put, the normal vector always points towards the concave side of the curve, as we can see. Now suppose we're given a smooth curve defined by the position vector function of the parameter t, rather than the arc length parameter s, then we can use the chain rule to rewrite the principal unit normal vector. So we can write n hat is dt with respect to t by dt ds using the chain rule, and that's divided by the magnitude of this vector. So using the chain rule, we can again write dt dt by dt ds. So the norm of a scalar multiplied by a vector is equal to the norm of the vector by the absolute value of the scalar. And given that dt ds is the reciprocal of ds dt, and ds dt is always positive for a smooth curve, then these two expressions cancel. So if we get rid of these terms, this is our principal unit normal vector written in terms of the parameter t. So we don't have to find the curvature or the arc length parameter first to find the principal unit normal vector in this case, where we're given r as a function of t, as we can obtain the unit tangent vector as a function of t from the velocity. The osculating circle, or circle of curvature, at a point P on a planar curve, where the curvature is not zero, is the circle in the plane of the curve that has the same tangent line as the curve at point P, the same curvature at P, and the center of this circle is towards the concave or inner side of the curve. Now the radius of curvature at point P is the reciprocal of the curvature at this point. And this is also equal to the radius of the osculating circle. And the center of curvature at point P is the center of the osculating circle. So the flatter the curve is, then the larger the radius of curvature. So if the curve has a smaller curvature at point P, then the osculating circle has a larger radius of curvature. But for curves that turn sharply, which have a high curvature, then the osculating circle will have a lower radius of curvature. So this osculating circle is not drawn to scale. The curvature, normal and tangent vector functions for planar curves are applicable to space curves. So we specified a space curve as a vector function of a parameter t, and given S is the arc length parameter of the curve, then a derivative of the position vector with respect to the arc length parameter is equal to the velocity vector normalized by its magnitude. And this is how we defined the unit tangent vector function. And the curvature in 3D space is the same expression for planar curves. So that was the magnitude of the derivative of the tangent vector function with respect to the arc length parameter, which is equal to the reciprocal of the magnitude of the velocity vector by the magnitude of the derivative of the tangent vector with respect to the parameter t. And we saw that the vector, being the derivative of the tangent vector with respect to the arc length parameter, was orthogonal to the tangent vector because the unit tangent vector has a constant length, being 1, and therefore the principal unit normal was equal to the reciprocal of the curvature by the derivative of the tangent vector with respect to the arc length parameter. And that's also equal to the derivative of the tangent vector with respect to t on the magnitude of this vector. So these are alternative expressions for the unit tangent vector, curvature, and principal unit normal vector in terms of the arc length parameter s and the parameter t. So noting that here v is a function of t. And now we'll apply these equations in practice problems. Give an anti-clockwise parametrization of a circle with a radius of ρ and find the curvature. Well, the position vector can be written as the radius cosine of parameter t in the I direction plus the radius by sine t in the j direction. And recall the curvature was equal to 1 over the magnitude of the velocity vector by the magnitude of the derivative of the tangent vector with respect to the parameter t. So v as a function of t can be obtained by differentiating the position vector function. So we get minus ρ sine t in the I direction plus ρ cosine t in the j direction. So the magnitude of v is the square root of minus ρ sine t squared, which is ρ squared sine squared t, plus ρ cosine t squared. So we have ρ squared cosine squared t. So using the trig identity, we get ρ. And the unit tangent vector is equal to the velocity on the magnitude of the velocity. So that gives minus sine t in the I direction plus cosine t in the j direction. And differentiating the tangent vector function, we get minus cosine t in the I direction minus sine t in the j direction. And therefore the magnitude of this vector is 1. And the magnitude of v we obtain as ρ. So the curvature is 1 on the radius of the circle. Find the unit tangent and principal normal vectors for the motion described by the following vector function. And we're given a base point at x equals 2 and y equals 0. So recall the unit tangent vector function was equal to the derivative of the position vector function with respect to the arc length parameter. So that gives minus sine s on 2 in the I direction plus cosine s on 2 in the j direction. And the principal normal vector is the reciprocal of the curvature by the derivative of the unit tangent vector with respect to the arc length parameter. And the curvature is the magnitude of this vector, dt hat ds. So dt hat ds is minus a half cosine s on 2 in the I direction minus a half by sine s on 2 in the j direction. So the magnitude of this vector is equal to the square root of 1/2 squared, which is equal to a half. So this makes sense because the radius of curvature of the circle is the reciprocal of the curvature, being equal to 2. So therefore, if we divide this derivative by the curvature, the 2's cancel, and we get minus cosine of s on 2 in the I direction minus sine s on 2 in the j direction. So note that the circumference of this circle is 2 pi by the radius, which is 4 pi. And therefore when the arc length function is equal to 0, so the directed distance from this base point is 0, we have the tangent vector having a component of 0 and 1 in the vertical direction. And the unit normal vector has a component of -1 in the horizontal direction and 0 in the vertical direction. Now when the directed distance s from the base point is equal to 1/4 of the circumference, being pi, then the unit tangent vector has a component of -1 in the x direction, and in the y direction, cosine pi on 2 is 0. And the principal unit normal vector has a 0 component in the x direction and -1 in the y direction. So note that when s equals 0, t is equal to 0 at the base point, and when s is equal to pi, t is equal to pi on 2 at this point. So we have a counterclockwise parameterization of the circle using the arc length parameter s. Find the curvature and principal normal unit vector for the helix. So the curvature is the reciprocal of the speed by the derivative of the tangent vector with respect to t. Given that the parameterization is in terms of the parameter t. And we can obtain v, being the velocity function, is minus sine t in the I direction plus cosine t in the y direction plus k. And therefore the magnitude of the velocity vector is the square root of sine squared t plus cosine squared t plus 1 squared, which is root 2, using the trig identity. And from this, we can determine the tangent vector, which is the velocity vector on its magnitude. So that gives minus sine t on root 2 in the I direction plus cosine t on root 2 in the j direction plus 1 on root 2 in the z direction. And differentiating the unit tangent vector, we get minus cosine t on root 2 in the I direction minus sine t on root 2 in the j direction plus 0 in the k direction. And therefore the magnitude of this vector is equal to the square root of 1 on root 2 squared, which is the square root of a half, or 1 on root 2. So the curvature of this helix is 1 on root 2 by 1 on root 2, or a half. And the principal unit normal vector is the derivative of the tangent vector with respect to t on its magnitude, which is equal to minus cosine t on root 2 over 1 on root 2. So the root 2's cancel, and we get minus cosine t in the I direction, and similarly minus sine t in the j direction.